Hi, everyone. My name is Michael Kennedy, and I'm in my fifth year here at UF getting my master's in aerospace engineering this fall, focusing on controls and orbital mechanics. I'll be helping Dr. Dong out this fall by covering some of the orbital mechanics topics related to this project. I'll be going through a review of the relevant astrodynamics theory needed for it, as well as the implementation of that theory by using STK to show you how you can visualize certain parts of the mission and create reports on how long certain things will take. I'll be mostly using my notes from when I took EAS4510 with Dr. Rao in spring 19, as well as an excellent book, Fundamentals of Astrodynamics by Bates, Mueller, and White. There was an original edition that existed for a long time. I think it was written in the 60s or 70s. And that one's still good. And both of that one and the new edition are pretty cheap. But if you can get a hold of the newer edition, I use it all the time as a reference for different classes and things with the work, even my internship this past summer. So it's around 20 bucks. Fundamentals of Astrodynamics. Second edition, you can get a hold of it. It's a lot better. They don't use feet and imperial units like they do in the first one. What about myself? I grew up in Boca Raton, Florida. And originally when I went to college, I wanted to study history, but I didn't want to write papers all the time. So I decided, because I was interested in the history of the Cold War and technology and things that happened around the 20th century, I should just try to join that field, actually. So made the jump and picked my bachelor's in aerospace engineering. That was the summer of 2017 and have not looked back since. I ended up liking it so much that I asked if they could let me stay for my master's, and here I am. Part of my motivation to stay for this extra semester, extra year almost, is to finish the small satellite project that we've been working on. I work as part of the Adamas lab under Dr. Ricardo Bevilacqua. You can see a picture of me with it on the top right. We actually just finished the thing off this past week, and it's a really cool project we've been working on. It'll be going to space this December on a SpaceX station resupply. Another reason I wanted to stay a little longer was to have another football season. Picture on the bottom left is me and my friends in Baton Rouge for the LSU game. Our junior year is fall 19. And I've gone to just about every home game, and as well as some of the bowl games and away games in my time here. Also, I'm a big runner. Picture me in the bottom right running the Gainesville half marathon. And this fall, I'm training to run a full marathon. The problem we're working on this semester is, astrodynamics wise, the interplanetary Holman transfer. Now, there's going to be a part of the problem we get to later on down the line where we go from Mars orbit to back and forth between the moons and determining how much that is. I'm waiting for Dr. Dong to get confirmation that we can get a hold of an STK license for everybody, because you need STK Pro to use STK beyond Earth, as well as to have maneuvers like docking, rendezvous and landing, things like that. This week's video, however, I'm going to be going over the math needed to more or less plan out your trip from an Earth orbit to a Martian orbit, as well as when this trip can occur. The trip from orbiting one planet to another is broken down into three phases: departure, heliocentric transfer, and arrival. And it takes the form of essentially a Hohmann transfer, same as if you're going from a lower orbit around Earth to a higher orbit. Difference being, we're all around the sun. To begin planning our journey, we have to make a few assumptions. The biggest one being that we assume both Earth and Mars are in perfectly circular coplanar orbits, no inclination around the sun. Both are circles. This isn't exactly the case, but the thing with both of these planets' orbits, as well as a lot of the other planets until you get really far out, is that their eccentricities are really low, as are their inclinations relative to the sun. So this won't be a huge issue here. And the fact of the matter is that with scales this big, being slightly off on the plane and things like that will not affect your overall delta V budget too big. And that's the main part of what I'm describing all this for. And the math used today will be, you can determine the delta V needed to get your EEV to Mars from Earth, and that satisfies one of the project requirements, which needs you to determine a launch vehicle and a launch time. So that's why we're covering this. We start by saying that our spacecraft orbit around the Earth from the greater perspective of this planetary transfer and around the sun is just an orbit around the sun, moving as fast as the Earth moves around the sun with the same radius as it too. This is because the speed and the altitude with which we're orbiting the Earth at the beginning, it's almost negligible when you think of the speeds with which these bodies orbit the sun. So the delta V required for the departure burn to leave Earth and have this orbit where you're around the sun, and the periapsis is the radius of the Earth's orbit around the sun, and the apoapsis is the radius of Mars' orbit around the sun, is the difference between the speed of the Earth around the sun orbitally and the speed of Mars, or actually, sorry, the speed of the transfer orbit, which is determined by this formula. Mu underscore sun is the gravitational parameter of the sun. And by using just the basic Coleman transfer formula and understanding that our semi-major axis, because the two orbits are circular, is just the sum of them halved, we get this formula for the delta V for your burn to leave Earth. Likewise, as it's a Holman transfer, you do your burn to achieve V1, and then you need to do your delta V2 to achieve your V2 where you're in the higher circular orbit. Same kind of thing there. This is the formula for that one. Now, by combining some of the denominators and putting it all together, the total velocity you're going to need to add to your spacecraft to get from your Earth orbit to being around Mars somewhere is answered by this equation. It's all just algebra. It's just, the kind of thing that you will then be able to use. You just rip it from this and determine what kind of energy you're going to need to add to get your EEV out to Mars and then around Mars. Additionally, the time it takes to get out there is pi times transfer orbit. It's normally 2 pi for the whole orbit, but this is going to be half your transfer orbit is what it takes to get out there. So now that you have these, you can, like I said, you can use the relevant values and determine what kind of a burn you're going to need to leave Earth and slow down at Mars. However, you can't just perform these burns whenever you want. You need Mars to be there when you're there. So to determine what conditions are right for an Earth-Mars transfer, we need to look at the phase angles, or the angular distance between the two planets relative to the sun. We'll denote the phase angle between Earth and Mars at any one time by lowercase gamma, gamma 1 in this case for this specific period in time. From this diagram, you'll see that the angle swept out by the transferring spacecraft from the Earth at its departure time to Mars at its arrival time, nothing more than the difference between the true anomaly at departure and arrival relative to the sun. With knowledge of the heliocentric transfer orbit, which we have from prior slides, these true anomalies can be found using the following. And these are values you can get, and assuming that these are both circular orbits, and you don't have to worry about the eccentricities, you can apply this to any one point. Through the Kepler equation as well, we know that angularly Mars will move at its orbital speed multiplied by this transfer time we discussed on the last slide for the transfer orbit. To ensure that our phase angle is correct at departure, we combine these two equations and get the following formula. So the time when you can go from Earth to Mars is whenever gamma 1 is equal to the difference in the true anomalies minus the angular rate Mars moves around the sun times the transfer orbit's time, which again will be a constant because we're assuming that these are circular orbits. And at any time you go from Earth to Mars, it'll be the same amount of time to transfer. Looking ahead, we'll be talking about in the future actually how to achieve the final Martian orbit you desire, as well as including the precision that comes with factoring in the eccentricities and inclinations relative to the sun of the two planets. From there, we'll be going on to using STK to model more in depth our mission and get some really cool animations to have for our PDR and CDR presentations. Thank you, guys.